Hello everyone, this is Shovik. Welcome to the one-shot video of rearrangement reactions part 2. So we will start the reactions named as Hofmann rearrangement. This is a rearrangement of primary carbamide to an isocyanate. Here, this is a amide, primary carbamide. It will be rearranged to isocyanate by reaction with sodium hydroxide as a base and bromide and bromine. So first it will now we'll see the mechanism of this reaction, of this rearrangement reaction. Sodium hydroxide will abstract the proton of this amide and it will lead to the formation of this anion. This anion will react with bromine and it leads to the removal of this bromide ion and it leads to the formation of in bromoamide. Again, this sodium hydroxide will abstract this proton and it leads to the formation of this anion, and this anion will rearrange like this anion will go. This minus charge will shift it to this carbon, and this alkyl group will shift to the nitrogen, and there will be removal of this bromide. So it leads to the removal of this bromide ion. So it leads to the formation of this isocyanate. This is isocyanate. Now, when we are reacting this isocyanate in presence of water, so it will give this amide. Next, if we are reacting this next in presence of heat, there will be removal of this CO2 and it leads to the formation of amine. Our next reaction is Cope rearrangement. This is a thermally induced 3,3 sigma-tropic shift of 1,5-diene to another isomeric 1,5-diene. Here you see, like in presence of one heating condition, it undergoes 3,3 sigma-tropic shift of 1,5-diene. Here you see this is 1,5-diene. 1, 2, 3, 4. No, this is 4, 5. So 1,5-diene. Now in present, so it is converted to the another 1,5-diene isomeric 1,5-diene. So 1, 2, 3, 4, 5. So this is the 4 examples of this Cope rearrangement reaction. So we'll see the mechanism of this rearrangement reaction. So we'll see the first example. This is the first example. So here we will write this structure like this, like in a 6-membered like in this 6-membered ring structure way. Okay, now what will happen now? Here you see that both methyl groups are trans to each other, and so here both methyl groups are trans to each other. Here this is trans, these methyl groups are trans to each other. This alkene also trans to each other. So it gives, so here, like, so these two methyl groups here, if you are converting these to the chair type of conformation, so here you see two this methyl groups is, and this methyl group are both opposite to each other. Now in presence of heat, it undergoes 3,3 sigma-tropic shift. Now what is the 3,3 sigma-tropic shift? Like this bond will break. Means this bond will break. Means 3,3 sigma-tropic shift means we need to numbering from which bond will break. From there we need to start numbering. This is, so this bond will break. So 1, 2, 3, and this side 1, 2, 3. So there will be ring bond formation between these 3. That's why it's called as 3,3 sigma-tropic shift. So how this bond is breaking? this bond will break. This bond will break, and it forms a bond from between this. This bond will shift it to here, double bond. So it leads to the formation of another 1,5 diene. Now here you see both methyl groups are anti to each other. So one methyl groups are above the plane and another methyl groups are below the plane. Next example is, this is the example. So here you see, here both methyl groups are both terminal methyl groups are seen to each other. So here you see, like, both methyl groups in the chair conformation, you see both methyl groups are seen to each other in chair conformation. These methyl groups will be above the plane. These methyl groups also will be the above the plane. Okay. Now when there will be upon heating, it undergoes 3,3 methyl 3,3 sigmatropic shift. So again this bond will break. So 1, 2, 3, and here this side 1, 2, 3. So this bond will break. This double bond will shift to each other here. So it will form bond between this carbon and this carbon, and this double bond will shift to here. This to the formation of this 1,5 diene. Here you see both methyl groups are seen to each other. Here both methyl groups are seen to each other. Okay. Another example, like here you see, both methyl groups are anti to each other, and these methyl groups are seen to each other. Okay, but when we are doing converting this to this, we are doing CC bond rotation. So during CC bond rotation, this methyl, these two methyl converted to the these two methyl converted to trans to each other, like two methyl converted to the trans to each other on CC bond rotation. Again, next we need to convert these to CR conformation. So here two methyl groups you see are both opposite to each other, and here also two methyl groups are both opposite to each other. Now upon heating, like, it undergoes C33 sigmatropic shift. So this bond will break, this bond will go here, will shift here, and this bond, double bond, will shift here. So it will form like this. Here you see, like, these two methyl groups are opposite to each other, and these two methyl groups are also opposite to each other. Now in this case, these two methyl groups are opposite to each other, and these two methyl groups are opposite to each other. Upon CC bond rotation, so these two methyl groups become cis to each, seen to each other. So, and these two methyl groups will be anti or trans to each other. Now we need to convert this conformation to CR conformation. Next, if we are heating this compound, so it will undergoes 3,3 sigmatropic shift, like this way, and it forms this compound. And if we will convert this to our normal structure, so it will be converted to, like, these two methyl groups are seen to each other. Here you see both are in the same phase, like same plane, like both methyl groups are in the same phase to each other, and these two methyl groups are anti to each other. So these two methyl groups are anti to each other. Our next reaction is oxycope rearrangement. This is a rearrangement of hydroxyl group attached to the sp3 carbon of 1,1,5-diene to an unsaturated carbonyl compound. So there will be like in cope rearrangement, this will be the 1,5-diene, but in case of oxycope, we will attach one more hydroxyl group in the sp3 carbon. So it will give unsaturated carbonyl compound. This is unsaturated aldehyde. So it undergoes, now in this case it undergoes 3,3 sigmatropic shift. 3,3 sigmatropic shift means this bond will break and this bond will shift, this bond will shift. So 3,3 sigmatropic shift, and it leads to the formation of this enol, unsaturated enol. Later it undergoes tautomerization to give this unsaturated aldehyde. Next next example is this example, like in this one also it undergoes 3,3 sigmatropic shift. So this bond will shift, this bond will shift, and this bond will break. So it will form this enol, unsaturated enol. Later it will form this unsaturated ketone. Now, in presence of a base, reaction proceeds at a much faster than the normal rate, than the normal condition. So if you are using any base, like here we are using the potassium hydride as a base, so it will abstract the proton. It will abstract the proton of the alcohol, and it leads to the formation of this oxide. Later it undergoes the 3,3 sigmatropic shift as we see here, and it leads to the formation of enolate. If we are protonating, like protonating this one, that is acid workup, if you are doing any acid workup, so it will convert it to the unsaturated aldehyde. But this, under this basic condition, reaction rate will be much more faster than the normal conditions, like normal heating conditions. Our next reaction is Claisen rearrangement. This is a thermally induced 3,3 sigmatropic rearrangement of allyl vinyl ether, which gives the gamma delta unsaturated ketone or aldehyde. Here you see, this is a allyl vinyl ether. Here you see, this is ether. This is ether, we know, like oxygen attached to alkyl group. So this is allyl ether, means allyl means this is the allyl group. This is allyl group, and this is vinyl group. This is vinyl group. That's why it is known as allyl vinyl ether. So under it was also undergo same type of 3,3 sigmatropic shift. So in this case, here we will convert this structure to like this. Like here you see both methyl groups are opposite to each other. One is below the plane, another one is above the plane. If you after this reaction, so if so under the thermal condition, it undergoes 3,3 sigmatropic shift. This bond will break here, this bond will come, this bond will shift here. Okay, and it will be converted to this gamma delta unsaturated ketone. Ketone. Here you see gamma delta unsaturated ketone means this is ketone, so this is alpha carbon, this is beta, this is gamma, this is delta. So gamma delta unsaturated ketone. So it forms gamma delta unsaturated ketone. Now in this case, here no hydrogen, no methyl groups are there, only hydrogen is there. So it we can write this structure like this way, and we can convert the structure to the chair like a conformation where both methyl groups are anti to each other. Now after if it will undergo 3 sigmatropic shift under the thermal condition, so it will give alpha beta unsaturated aldehyde. This is alpha beta gamma delta. So gamma delta unsaturated aldehyde. Our next reaction, our next example is, this is also example of a Claisen rearrangement. So it is also a ether, allyl vinyl ether. This is vinyl group, like this is vinyl group, and this is allyl group. This is allyl group. This is allyl group. Okay. So in presence of heat, and that is thermal condition, it will undergo 3 sigmatropic shift. Now how it will undergoes? Now we need to give a numbering here: 1, 2, 3, and this 1, 2, 3. So 3 sigmatropic. So here will be making of this making the bond between these two carbon. So it will there will be shifting of double bond like this. So double bond shift here, this double bond will shift here, and this double bond will shift here. So it leads to the formation of this ketone. Next, in presence because this is unstable one ketone, so it undergoes tautomerization to enol. So enol means it becomes an aromatic system, which is a stable one. So it forms alpha beta. This is alpha. This is alpha beta gamma delta. So it will be gamma delta unsaturated alcohol or enol. Our next rearrangement reaction is Johnson-Claisen rearrangement. This is a thermally induced reaction of allylic alcohol with trialkyl orthoacetate under the acidic condition, which produce gamma delta unsaturated ester. So this is a allylic alcohol. This is allylic alcohol. Yeah. So, and in presence of this trialkyl orthoacetate, this is trialkyl orthoacetate, it gives this alpha gamma delta unsaturated ester. Means this is alpha, this is beta, this is gamma, this is delta. So it will be gamma delta unsaturated ester. In presence of any like amine, like if we are substituting this on alkoxy group like OR group, this if you are substituting one OR group to NR2 like any amine, and then it will be converted to here amide. will convert it to one amide, not ester. It will be amide, gamma delta unsaturated amide. In this case also same ester. This is also ester. Now we will see the mechanism of this reaction. So the trialkyl orthoacetate will react, will abstract the proton from acid, so it will form this carbon ion. Now we it on alkoxy ion, alkoxy group will have one lone pair on the oxygen, so it will abstract, so this lone pair will shifted here, and this bond will break, and there will be removal of the alcohol, and it forms this carbocation. Now in presence of this allyl alcohol have lone pair of electron. This lone pair of electron attack on the carbon of this carbocation, and this bond will shift here, and it leads to the formation of this intermediate. Next step is, like, we have this intermediate, so this intermediate OR have one lone pair, so this lone pair will shifted to here, and there will be removal of this alkoxide ion, and this so it will form this carbon ion, like carbocation, this carbocation. Now there will be removal of this H plus, and this bond will shift here, so it will form this alkene here alkene. Now here, if you are seeing carefully, so you will see like 1,3,3 sigmatropic shift will happen if you are hitting this intermediate. So here you see, like, we are giving numbering from here 1, 2, 3, and 1, 2, 3. So this bond will break. This bond will break, and it will shift. It will attach to here. This bond will break, and it will be shifted here, and this bond will break, and it will be shifted here. So it will give this gamma delta unsaturated ester. And here you see, like, there will be retention of configuration. Here CH2, here ester CH2, which is CH2 with ester is coming in the same plane as this hydroxyl group. So there will be retention of configuration. Now in case of, if we are in place of any in place of trialkyl orthoacetate, if you are in this case, if you are substituting this alkoxy group to the amine, then how reaction will happen. So first it will abstract the proton, who like oxygen and lone pair will abstract the proton from system, and it will give this carbocation. Next, oxygen have lone pair, so this lone pair will shift it here, and there will be breaking of this bond, so it gives this carbocation. Now in presence of allyl alcohol, this carbocation which will be formed, it will react, like oxygen will attack on the carbon atom of the of this carbocation, and this bond will shift, and it leads to the formation of this intermediate. And next, nitrogen have lone pair, nitrogen lone pair will shift here, and there will be removal of the alkoxide ion. Now it leads to the formation of this carbocation. Now there, if if under this, if you abstract this proton, so it leads, this bond will shift here, and it leads to the formation of this alkene. Now under the heating condition, so it will undergo 3,3 sigmatropic shift here, 1, 2, 3. So this bond will go attack here, this bond will go, and this bond will go. So it forms a gamma delta unsaturated amide. Next, our next reaction is Ireland Claisen rearrangement. This is allyl ester of this is a reaction of allyl ester of carboxylic acid. This is carboxylic acid. Like if you are doing this is carboxylic acid. Now, if you are adding this allyl in place of if you are replacing this with allyl group, this is allyl group. So then it becomes allyl ester of carboxylic acid, and so here allyl ester of a carboxylic acid converted to its silyl enol ether. This is silyl enol ether. It will rearrange to the 3,3 sigmatropic shift under the thermal condition. Under the thermal condition, it undergoes 3,3 sigmatropic shift to give gamma delta, that is here gamma alpha, beta, gamma delta. It gives gamma delta unsaturated acid. Now we will see the mechanism of this reaction. First we are using LDA. So LDA will act as a base. So LDA means lithium diisopropyl amide. So this is lithium diisopropyl amide. Will abstract the base, and this it will abstract this proton, and it leads to the formation of this lithium enolate. Okay, this is lithium enolate. Now lithium enolate present as O minus L plus. So this O minus will attack on the TMS chloride, that is trimethyl silyl chloride, and it will give this silyl enol ether. Silyl enol ether. Now we will convert this structure to the chair conformation. So it will be look like this. So here under the thermal condition, it undergoes with 3,3 sigmatropic shift. So 3,3 sigmatropic shift means in 1, 2, 3. Here 1, 2, 3. So this bond will break and this bond will form. So it will be acting like this bond will break here, this bond will shift here, this bond will shift here. So it leads to the formation of this CO2 TMS. If we are doing any proton like acid workup, so it will be converted to gamma delta unsaturated acid. This is a Eisen-Moser fragmentation of hydrogen. This is a fragmentation of hydrogens of alpha beta epoxy ketones. So this is first of all, fragmentation means there will be fragment like one structure. If we are considering this and this cyclohexane structure, so fragmentation means there will be breakage of this making of the fragment of like it this structure will be fragmented into a number of species. That means the fragmentation. Okay, so fragmentation, so it is a fragmentation of hydrogens of alpha beta epoxy ketone. So this is alpha beta epoxy ketone, means this is alpha, this is beta. So alpha beta epoxy ketone. So in presence of tosyl hydrazone, like tosyl hydrazine, this is tosyl hydrazine, it undergoes a reaction with this ketone to form this tosyl hydrazone. In presence of sodium methoxide, that is acting as a base here. This is sodium methoxide will act as a base, and it will be converted to this It will be fragmented like ketone, alkylic ketone, alkylic, like alkylic ketone. Now we'll see the mechanism of this reaction. So we'll start with tosyl hydrazone. So we are using here sodium methoxide as a base. So sodium methoxide will abstract the proton of the tosyl hydrazone, and this there will be removal of this proton, and it leads to the formation of this negative ion, that is negative, that is anion. This anion will shift here. This anion will shift here, and this bond will shift here, and this epoxide bond will break, and it leads to the formation of this alkoxide. Next step, like this bond will break, this anion will shift here, this bond will break, so to form alkyne. Next, this bond will break and form nitrogen, and this bond will break, there will be removal of nitrogen and tosyl ion. So this will form this alkyl ketone. Next rearrangement reaction is Demyanov rearrangement reaction. This is a ring expansion or ring contraction of cyclic carbocations. So here we are using like cyclobutane, cyclobutylamine. So in presence of sodium, sodium nitrate, and HCl, it undergoes diazotization. This is diazotization. So it will form diazo compound. Now it will present as N2 plus and Cl minus. If it and this bond will break, and it leads to the removal of this nitrogen. So it leads to the formation of this carbocation. So there is a possibility like this carbocation will stay like this, like will will be stable like this, or there will be ring contraction, like this bond, this ring will be bond will be shifted to here, so it will form this cyclopropyl ring. Now in presence of H2O, like if we are giving H2 as a solvent, so it will give these two type of alcohol. So in presence of this, in case of this compound, we are getting these two compound, like one is ring contracted product, another one is normal product. Our next example is like sodium nitrate and HCl. It undergoes diazotization to give this diazo compound. Now there will be removal of nitrogen, and it will give this primary carbocation. Now this primary carbocation is very unstable, so it undergoes ring expansion. So it will convert it to the that is, this bond is shifted to this CH, that this methylene carbon. So it will form this this ring expanded cyclohexane cyclohexane ring. Now there will be removal of this proton, like which is present like this. So this bond will break, and it leads to the formation of this cyclohexanone. Our next example is this like two bromo compound, like or two halo. So in presence of this Grignard reagent, so it will be present as isopropyl plus and MgBr minus, isopropyl minus MgBr plus. So isopropyl minus will abstract the proton of alcohol, and it leads to the formation of this alkoxide ion later, like like it will form like this way, alkoxide ion. So first there will be removal of bromide. So it will form this carbocation. Okay. Next, if you are doing any ring expansion, so it will ring expanded to 7-membered ring. So it will be converted to this. So at the end it will form like ring expanded product, that is cycloheptanone. Now in this another example is that is dibromo compound. So in presence of silver nitrate, aqueous silver nitrate, so it will be silver nitrate present as silver plus, nitrate minus. So bromine have lone pair of electron, so it will abstract the silver ion. So it will form this carbocation. There will be removal of this silver bromide, and it leads to the formation of this cyclopropyl carbocation. And this is a very unstable, because of this 3-membered cyclopropyl ring, that is ring strain. So ring strain will be relieved by shifting of this bond here. So it leads to the formation of this cyclohexene carbocation. Now in presence of water, because we are using aqueous silver nitrate, so there will be some water will be there. So this water will react on with this carbocation, and it leads to the formation of allylic alcohol. Our next reaction is Neber rearrangement. This is a base catalyzed conversion of O-tosyl oxime, and it leads to the formation of alpha amino ketone. That is O-tosyl, like this is O-tosyl oxime. O-tosyl, this is oxime. This is a normal oxime. We are doing tosylation of this oxime to form tosyl oxime, O-tosyl oxime. Now in presence of base, it will converted to alpha amino ketone. Now we will see the mechanism of this reaction. So this is O-tosyl oxime. So we have base on the system. So base will abstract this proton, and it leads to the formation of this anion. Now this anion will attack on the nitrogen, and there will be removal of this tosyl OTS group, OTS minus anion, and it leads to the formation of this aziridine. Next, in presence of water, water will attack on this double bond, that is aziridine. This double bond will open up, like double bond will shift it to the nitrogen, and it will form this intermediate. Now this OH bond will break, and this bond will break, and it leads to the formation of like R NH minus CO R dash. Now if you are doing any acid workup, so it will be converted to this alpha amino ketone. Our next reaction is benzene rearrangement. This is an acid catalyzed conversion of hydroazobenzene to benzene. So this is hydroazobenzene and this is benzene in presence of acid like H plus. So we will see the mechanism of this reaction. This is hydroazobenzene. Hydroazobenzene. So as we know the azobenzene, azo means in, double bond in. Okay. Hydroazo means this double bond will be reduced to NH, here NH. So that means hydroazobenzene. So in presence of H plus, like acidic medium, both nitrogen will abstract the proton from the system and it leads to the formation of this double carbocation, which is very unstable intermediate. So this bond will break, this bond will break, this bond will break, this bond will break, this bond will shift it to here. So it leads to the formation of this intermediate. Next step, like we can write this structure like this. Now if there will be removal of another H plus, 2 H plus, like this H plus, if it will be removed, this bond will break, form bond here, this bond will break, this bond will shifted to NH2 plus, and if this bond will break, this bond will shifted to here and this bond will be shifted to NH2 plus, so it will form this benzene.